Hello, welcome to the slide-based presentation of formal languages and automated theory. Today we will look at a very important concept in the theory of computation, namely the use of reductions to prove that certain languages are undecidable or not recursive. I start with a little bit of recapitulation. So recall that we have proved that any Turing machine can be encoded in binary, and any input for that machine can also be encoded in binary. This enables us to define two important problems in this context. The first one is called the membership problem, which accepts as input a Turing machine M, or more precisely the encoding of a Turing machine M, followed by a separator hash, followed by the encoding of an input for M. And this language consists of all those pairs M and W, such that M accepts the input W. Likewise, we can define a halting problem as the language of all M-W pairs, such that M halts on input W after accepting or explicitly rejecting. Now, we have defined a Turing machine to be a decider or a total Turing machine if it halts on all inputs. As you can see, this membership problem and the halting problem, they are both Turing recognizable or recursively enumerable, because a Turing machine can emulate the work of this machine M on input W and accept if M accepts W or halts on W, depending upon which problem you are going to recognize. And though they are recognizable, we have already proved by using a diagonalization argument that the halting problem is not recursive. In other words, no matter how intelligent Turing machines can be, you cannot design a decider, that is a total Turing machine, for the halting problem. A very similar diagonalization argument can be made to prove that the membership problem is also not recursive. Okay. Now I will show an alternative way of proving the membership problem to be non-recursive. This is by using what is called reduction. Okay. So we will do what we technically call a reduction from the halting problem to the membership problem. In other words, given an instance M hash W for the halting problem, we want to convert that instance to an instance N hash V for the membership problem, such that N accepts V if and only if M halts on W. Okay. So, if we assume that a decider exists for the membership problem, then this reduction algorithm followed by this decider gives us a decider for the halting problem. Okay. This decider for the membership problem says yes or no for every input in a finite amount of time. Therefore, if I use this as a subroutine in tandem with this reduction algorithm, then I have a decider for the halting problem. One thing that you need to understand is that this reduction, or this conversion of M hash W to N hash V, must be doable by a total Turing machine. That is a Turing machine which always converts this to this for every possible input. This conversion algorithm stops after correctly making this conversion. So, if we have such a reduction algorithm and if we have a decider for the membership problem, we have a decider for the halting problem. But we have just proved that the halting problem is not decidable. Okay. So this gives a contradiction that a decider for the membership problem exists. Okay. So the membership problem is also undecidable or not recursive. So how does this reduction algorithm look like? Let us see. So as you see in this picture, the reduction algorithm takes as input an instance for the halting problem, that is M and W. It outputs an instance for the membership problem, that is N and V. Okay, so the reduction problem, the reduction algorithm can use this M and W to construct N and V. Okay, so it makes some small changes to M to convert it to N. So these changes are now like this. It adds a new accept state T prime and a new reject state R prime to this M. Of course, this M also had some accept state T and some reject state R. So these are now marked as ordinary states, that is non-halting states, neither accepting nor rejecting. And then what this reduction algorithm does, it adds a transition. If M is in state T, no matter whatever it scans from the tape, it always changes to this T prime and accepts, and after making one right movement. Likewise, whenever the machine M reaches the state R, reads whatever from the input, it immediately goes to T prime and accepts. And we take this V same as this W. Okay, now convince yourself that a total Turing machine can make this transformation from this to this. Now the property of N is that only way N can reject is by looping, because we have not added any transition from any state to R prime. Okay. On the other hand, if M halts after accepting in state T or rejecting in state R, then N just needs one more step to jump to this T prime and accept. Therefore, it follows that if M halts on W, then N accepts its input V, which is same as W anyway in this case. On the other hand, if M loops on W, that is, it rejects W, it's a case of implicit rejection, then N also loops on W and rejects W, that is same as V. So this reduction is perfect and proves the undecidability of the membership problem. Okay, so one very important thing is the direction of reduction. So this is the important topic, from which problem to which problem. Now this reduction, you want to prove certain problem to be undecidable, and you are given some problem which is known to be decidable. So reduction should take place from the problem which is already known to be decidable to the problem which you want to prove to be undecidable. For example, if I take a reduction in the opposite direction, that is from the membership problem to the halting problem, we can propose a valid reduction like this. Now the input is M hash W. This is an input for the membership problem, and we will produce an output n hash v for the halting problem. Okay, this can be done this way. Now keep the accept state t of m as it is. Okay, so n, whenever m jumps to t, n also jumps to t and accepts. But the reject state of m is now marked as a normal state. Okay. Instead, you create a new reject state r prime for n, and whenever m goes to the state r, then at that point of time, irrespective of whatever is on the state, the tape, it will keep on looping. Okay. So it will stay in state r. So we do not propose any transition that lets n to go to the new reject state r prime. And as usual, you take v equal to w. You can see that this has the property m accepts w if and only if n halts on v, because there are no transitions from any state to r prime. This is definitely a valid reduction. The problem is that this reduction cannot be used for proving the undecidability of the membership problem. The reason is that although this is a valid reduction, any decider for MP is not bound to use a decider for the halting problem. On the contrary, if we have earlier proved this membership problem to be undecidable, this reduction can be used to prove the undecidability of the halting problem. Yeah. So this is our first examples of reduction. Let us come to a formal definition. What we mean by reduction. Suppose that A is a language over some alphabet sigma, B is another language over some alphabet lambda. A reduction from A to B is a map, let us call it sigma, from sigma star to lambda star. It has the property that whenever I have a member of A, this will map to a member of B, and wherever there is something outside A but in sigma star, this will map to something outside B but in lambda star. So if W is in A, then its image will be in B. If W is not in A, then its image will also not be in B. Now this is not needed to be injective. And we want this sigma to be realized by a Turing machine. So it is something that a Turing machine can do. More importantly, on every input W, this Tm that converts some W to sigma of W must halt after correctly computing this image. I will call this R, this Turing machine R, a reduction algorithm. We say that sigma is a reduction from language A to language B. And we write this as A less than equal to B. This M sometimes we write as a subscript to indicate that this is a many to one reduction. Look at this, for example, this goes to this, this goes to this, so this is many to one reduction. Here also this goes to this and this also goes to this. And also we sometimes explicitly say Tm here to understand that this is a Turing reduction. The implication of this less than equal to sign is that this shows that the membership problem for A is no more difficult than the membership problem for B. And here are two examples. We have already seen two examples of reductions. The halting problem reduces to the membership problem, and also the membership problem reduces to the halting problem. Okay, so in order to explain this less than equal to sign, let us look at this real life example of reduction. Okay, so there is a room containing a table, a bucket and a tap. The mathematician is asked to put the bucket full of water on the top of this table. What he naturally does, he goes to the tap, fills the bucket with water and then puts the full bucket on the top of the table. On another day, the mathematician is asked to do the same thing, put a bucket full of water on the top of the table, and he enters the room. This time he finds that the bucket is already full of water. What he does is, he just drains out that water from the bucket, and then the situation he faces is like this. So the mathematician is now very happy to declare that, okay, I have reduced my new problem to the old problem, which I know how I can solve. Okay. Yeah, so reduction is a very powerful tool and you have to use it with caution. Definitely, we are talking about reducibility of languages. We can also talk about the reducibility of problems. In fact, we can always identify a language L by the membership problem. Given W in sigma star is W is in L. This is a problem, L is a language, a set. So whenever we have a reduction from one language to another, we can also talk about the reduction of the membership problem of the first language or the source language to the membership problem of the target language. So for problems P and Q, we will also freely write P less than equal to Q. Okay, and this is a very important thing. The only task that a reduction algorithm does is convert an instance for P to an instance for Q. It makes no effort to solve P or to solve Q. Okay, so it suffices to give a description of how an instance of P can be converted to an instance of P. We have seen this couple of examples on how this is done at some state, at some new transitions and all that stuff. But we never tried to solve the halting problem of the membership problem. Okay. But in future, what will happen, P and Q will be related to something like machines. So when we make a reduction from this to this, we will typically say how this target thing behaves, which is usually a Turing machine, possibly a Turing machine followed by an input, like that. And we will typically say how this machine behaves. We will not try to solve it, we will just say how it behaves, and we will keep to our imagination how this reduction algorithm works. What it does, that is the important thing that we will explain. We will soon look at some other examples soon. Now reduction can be used for a couple of purposes. First, if we can solve Q, then we can use this solver for Q as a subroutine to solve P in tandem with this reduction algorithm. In other words, if Q is solvable, then P is also solvable. Okay. But one thing you must remember, that this gives one way of solving P, and that way need not be the only way to solve P or the most efficient way to solve P, as the joke also illustrates. And second thing, this says that if Q is solvable, then P is also solvable. Solvable you may take in this context as decidable, and the contraposition of this implies that if P is not solvable, then Q is also not solvable. Or in terms of decidability, if P is undecidable, Q is also undecidable. And that happens only when you take a reduction from P 2q. So let us see a more serious example of reductions. So you want to prove that the problem whether a given Turing machine accepts the null string is not a solvable problem or is not a decidable problem. So this reduction mechanism is something like this. We will make reduction from the halting problem to this new problem. So the reduction algorithm takes as input an instance for the halting problem, which is a Turing machine M, and an input W for M. It converts it to an instance of this problem whether a Turing machine accepts the null string. So it will be a Turing machine N. And the property of this reduction will be M halts on W if and only if N accepts epsilon. Okay. This reduction algorithm must ensure this. So the input is M and W, an instance of the halting problem, and the output is a Turing machine that accepts epsilon if and only if M halts on W. So the steps, this is an important thing, as the picture also says that the reduction algorithm takes M and W as input, so it can hardware this M and W in the description of N, that is in the finite control of N. In other words, N can use M and W in any manner it likes to use. And this is a finite thing, description of M, the description of W. So this knowledge of M and W can be embedded in N's finite control because it's after all a finite amount of information. Okay. So I will just describe how N behaves on an input W, on an input V. W is an input for M, but N is an independent machine. It has another input V. And I leave it to yourself to imagine that a Turing machine given the description of M and W can produce a machine N which works as follows. N simply erases its input V. It has no real work on V. Instead, what it does, in its head, that is in its finite control, it has an information of M and W. So it writes that W from its finite control to the tape and it simulates M on W. If that simulation halts, the machine goes to the accept state. Whatever the accept state for this N is, not M, it goes to the accept state of N and halts. Now let us see that this reduction is perfect. N accepts its input only when the simulation stops. That means only when M halts on W. Likewise, if M halts after accepting or rejecting, does not matter, N simply goes to accept V. Therefore, it follows that the language of N, if M halts on W, then the simulation will eventually stop, and irrespective of whatever the input V is supplied to N, it will accept it here. This is true for any V. Therefore, if N halts on W, the language of N is sigma star. On the other hand, the simulation does not halt, then irrespective of what this V is, the simulation will keep on continue, that is N will also loop in this simulation. And it will never get the chance to come here and accept the input V. So in this case, its language is empty. Okay. In particular, sigma is a member of epsilon is a member of sigma star. So if M halts on W, N accepts epsilon. If M does not halt on W, then it accepts nothing. In particular, it also does not accept epsilon. Okay, so this reduction is perfect. And the same reduction can be used to prove that there are many other problems that are undecidable. For example, if we replace epsilon by any fixed string like 10111, something like that, then the problem whether this a given Turing machine accepts 10111 is undecidable. So like epsilon, 10111 belongs to sigma star but not to the empty set. So exactly the same reduction works. Likewise, the problem whether a given Turing machine accepts any string at all. If it accepts sigma star, of course it accepts any string. If it accepts only the empty set, then it accepts nothing. So the undecidability of this problem can also be proved using the same reduction. The problem whether a given Turing machine accepts all strings, that is, if the language of M is sigma star or not, that can also be decided. That can also be decided if we have a reduction. It's also, I would say, it's not decided. This problem was also undecidable. The same reduction proves it. The problem whether a given Turing machine accepts only finitely many strings is undecidable. Why? Because phi, the empty set, is a finite set, whereas sigma star is infinite. Now we see a second similar example of reduction. I will show that the problem whether the language of a given Turing machine M is regular is undecidable. Once again, so it's not the question whether it accepts something or accepts everything. I want to find out whether a Turing machine accepts a regular language. That is also undecidable. So once again we will use reduction from the halting problem, and this reduction is slightly more complicated. So once again the input, okay, so we will make a reduction from the halting problem to this new problem. So the reduction algorithm will take an input which is an instance for the halting problem, that is M and W. It converts that to the description of a language, and since M and W are input, the reduction algorithm embeds the information on M and W with the finite control of N. In addition, it embeds some other information which is marked here as U. In the earlier reduction, this U was not present, but now I am going to use this U. Okay, so the input for this reduction is an instance for the halting problem M and W. A Turing machine N is the output whose language is regular if and only if M halts on W. So M and W can be embedded in the finite control, and as the picture says, another extra information U is also embedded in the finite control. So it embeds the information of another fixed Turing machine in the finite control. So how is this U defined? So take any language L that is recursively enumerable but not recursive. We have seen quite a few examples of such languages: the halting problem, the membership problem, and two other examples. So in particular, we can take U equal to this language, we can take L equal to NP, the membership problem, in which case this U stands for the universal Turing machine. It is once again a Turing machine, it's a fixed Turing machine, the universal Turing machine, and the information about U, its transitions, its states, all these things fit in a finite amount of space and therefore can be embedded in the finite control of the output machine N. And the behavior for N is like this. upon input, n has an input v, m has an input w, but n has an independent input v. It does something slightly more complicated than in the reduction example 1. It immediately does not work on its, I would say, input v, but stores in a separate tape or track for use later, and then it copies w to its step, first step. This is stored in a second step, and this is stored in the first step, and this machine n simulates m on w. If the simulation halts, then the machine looks at v, and it simulates that other Turing machine u on this v, u, maybe the universal Turing machine on v. And if that simulation accepts v, then n accepts. Okay. So now let us see the situations when n accepts. N accepts its input v if and only if both the following conditions hold. That is, it should be able to come out of the simulation of m on w. Likewise, it should also be able to come out of the simulation with an accept notification. Right. So if m halts on w and u accepts and halts on v, then and only then n accepts v. Therefore, I can write, if m halts on w, then this condition is satisfied, and therefore the language of n is the same as the language of u, which is L. On the other hand, if m does not halt on w, then this simulation never ends, and irrespective of whether u accepts v or not, the simulation never gets a chance to come to this third step. So, its language is empty. Now, the original problem was n should have a, if m halts on w, n, the language of n should be regular. If it does not halt on w, then its language should not be regular. But what we have done is just the opposite thing. Okay. But this does not matter. Okay. If a decider exists for this problem, we can anyway flip the decision of the decider and do just the opposite of the decider. Okay. So, yeah. So, I would say, output should be a Turing machine whose language is regular if and only if m halts on w. But if we do it just the other way, a Turing machine whose language is not regular if and only if m halts on w, this is also fine. Okay. And this is what we have done precisely in this context. Also note that this L is chosen to be a language which is recursive but not recursively enumerable. In particular, it is not that L is not regular, L is not finite, L is not context free, L is not context sensitive, L is not recursive. Okay. Whereas this empty set is all of this: finite, regular, context free, context sensitive, and recursive. Therefore, the same example can be used to prove, same reduction example can be used to prove the following undecidability results. That is, the problem whether the language of a given Turing machine is finite. Of course, we have proved it in another way, but this is also fine. We can use also this example too. Whether m accepts a context-free language, that's also undecidable. A context-sensitive language, that is also undecidable. a recursive language that is undecidable. Okay, using the same reduction, we can prove all these 4 propositions. However, if I replace this thing, finite, regular, by recursively enumerable, problem whether the language of a given Turing machine is recursively enumerable, this is trivially decidable because M is a Turing machine, therefore its language has to be recursively enumerable. So this problem is trivially solvable. Its answer is always true. Okay, so we will proceed with more results on reduction after a small break. So let us stop for a moment for now.